Welcome to this explainer. Today, we're building a highly practical, step-by-step toolkit for minimizing your transport costs through really effective route design. Look, if you deal with physical logistics, mastering these concepts isn't just helpful, it's absolutely essential for your bottom line. Let's get right into it.
We have to start with a harsh reality. Transport is typically the single largest component of your total logistics cost. Number one. Every truck you send out, every mile driven, and every minute spent on the road eats directly into your profitability.
The politician Tim Kaine actually hit the nail on the head when he said, "You have got to connect your land use decisions with transportation decisions." Transport isn't merely a cost center or some operational afterthought you deal with later. It's a strategic choice. It can absolutely drive your competitive advantage. It's all about having the right route, the right strategy, and the right vehicle at the exact right time.
So, here's our syllabus for today's tutorial. We're going to look at the transport cost problem, apply some key route design principles, solve single and multi-origin transport problems, tackle the famous traveling salesman loop, and finally figure out how to choose your transport strategy.
Starting off with Part 1, the transport cost problem. Let's establish a solid baseline for why transport cost optimization is the biggest lever you can possibly pull in your operations.
The whole objective of route design is incredibly focused. We want to maximize transport efficiency, right? And we do that by minimizing three specific things: the number of vehicles required, the total distance traveled, and the total time taken. The core takeaway you need to remember here is that every additional kilometer, every extra hour, or an unnecessary vehicle is a heavy cost that you've got to earn back through service.
Moving on to Part 2, applying route design principles. Let's dive into the best practices and practical rules of the road for designing efficient delivery routes. Before we get into any complex math, you really should commit these 8 best practice principles from Baloo to memory. They're basically the foundation of our tutorial today. First, you want to cluster deliveries that are physically close together and separate your daily demands so different routes don't overlap. Always start building your route from the furthest customer first. Crucially, sequence those stops so the overall shape forms a teardrop. For the bigger picture, use single trips for large loads and make your pickups en route rather than retracing your steps. Finally, right-size your operations by outsourcing the tiny deliveries and widen those narrow time windows wherever you possibly can to cut down on risk.
Now that teardrop concept requires some serious disciplined sequencing to shorten your total distance. By mapping out points sequentially in an overlapping loop format, you ensure shorter distances and fewer vehicles. Plus, you avoid unnecessarily crossing your own paths, which is a huge waste of time.
So how do we apply these principles without buying complex software? We use the sweep method. It's a super intuitive manual heuristic. Step 1, just map all your customer locations and order quantities. Step 2, imagine a radial line extending from your depot and sweep it clockwise, kind of like a radar. As you sweep over customers, assign them to a vehicle. Step 3, you stop loading the exact moment that vehicle hits its capacity. And Step 4, sequence the stops within that vehicle's route using our teardrop principle. It's incredibly simple, but it typically gets you within 10% of a computer-optimized solution. How cool is that?
All right, Part 3, solving single origin routes. We're going to use the shortest route method to solve our first major type of transport problem together. So, transport problems are generally classified by their origins and destinations. A Type 1 problem is your standard single origin to single destination scenario, point A to point B. To solve this, we use the shortest route method. The concept here is pretty straightforward. You just evaluate the network to find the absolute shortest connected path of minimum distance, time, or cost. If we look at a sample network moving goods from point A to point H, the basic procedure is to enumerate every single feasible route. When we do the math on the 5 candidate routes here, we instantly see that Route 1, traveling through nodes B, E, and G, is the clear mathematical winner at 101 kilometers. It easily beats out all the other paths, which range all the way up to 144 kilometers. Simple direct comparison solves Type 1 every time.
Next up, Part 4, solving multi-origin transport. This is where things get significantly more complex. With a Type 2 problem, you have multiple origin points feeding multiple destinations. Think of multiple manufacturing plants supplying a network of regional warehouses. It's a lot to manage. To solve this, we use the transportation method, which is a 2-stage, grid-based mathematical approach. It helps us establish an initial supply flow and then optimize it.
Let's imagine a company, MBS,
supplying 3 different warehouses from 4 manufacturing plants. We start stage 1 with the northwest corner method. We literally begin allocating supply to demand in the top left or northwest cell of our matrix. We assign as much as possible, move to the right when a destination is full, and move down when a source is totally exhausted. By multiplying those allocated quantities by the unit cost of each route, we get an initial feasible total cost of 19,200 baht. But remember, this is just our starting point. We can do better.
That's where stage 2 comes in, using the stepping stone optimization method. This systematically tests every empty cell in our matrix by tracing a closed loop to see if moving our allocation there would actually lower costs. After running just 2 iterations of the stepping stone method on the MBS network, we reallocate the flow and drop the cost from 19,200 down to 17,900 baht. That is a massive 6.8% saving on transport essentially overnight just by optimally solving the math.
Let's move to Part 5, the traveling salesman loop, Step 3 in our problem-solving toolkit.
A Type 3 problem is a closed loop, meaning the start and end points are exactly the same. You probably know this universally as the traveling salesman problem, or TSP. The goal here is to hit every single customer stop exactly once, without backtracking, keep it at the minimum total distance, and then return home. Because this requires a complex distance matrix and gets computationally heavy very fast, we usually rely on heuristics to figure it out.
The absolute most practical way to solve a TSP manually is the nearest neighbor heuristic. You just start at the origin, find the shortest distance to the nearest unvisited location, move there, and repeat until everyone is visited before finally returning home. In a recent case study plotted for 8 scattered customers, applying this exact logic step by step optimized the total route down to a super tight 640-kilometer round-trip tour.
Which brings us to our final section, Part 6, Choosing Your Transport Strategy. With our routes beautifully calculated, let's look at the macro strategies for physical deployment.
Depending on your volume and geography, you generally have 3 primary strategic options. Direct shipment is point-to-point. This is ideal for full truckloads where speed is critical and you don't need any intermediate stops. Then you've got a milk run, which uses one vehicle to consolidate multiple small stops, either from several suppliers or to several customers. That lowers your total costs by spreading them out. Finally, cross-docking uses a distribution center purely as a transshipment point. Goods arrive, they get sorted, and they leave within 24 hours with absolutely zero storage cost. The crucial thing here is knowing exactly when to deploy each of these networks.
To make that decision, we have to match the transport strategy directly to the product profile. This 2x2 matrix is incredibly useful for that. If you have a high-demand, high-value product, like a flagship smartphone, you're going to keep central stock and use fast transport. But if you have high-demand, low-value items like everyday soap, you definitely want to stock close to the customer locally to save on those transport costs. Basically, different products demand completely different logical networks.
Cost is the lever we're always trying to pull down, but customer service will always be the constraint that limits us. We've built a really powerful toolkit today, from the teardrop principle all the way to the stepping stone method. So I'll leave you with this provocation to analyze your own operations. How much overhead could you eliminate by applying these exact principles and solving these transport problems in your business tomorrow?